How does strain hysteresis reveal material memory? Imagine bending a paperclip back and forth and noticing how it doesn't quite go back to its original shape perfectly. That's a simple way to see how materials remember past deformations. When we look at how materials stretch and relax, a fascinating pattern emerges called strain hysteresis. This pattern shows up as a loop on a graph that plots stress against strain during loading and unloading. Instead of a straight line, the loop indicates that the material's response depends on its previous history, not just the current load. When you stretch a material, it deforms elastically at first, meaning it returns to its original shape when you releases it. But if you keep stretching, it might undergo plastic deformation, which causes permanent changes. When you releases the load, the material often doesn't follow the same path it took when stretching. Instead, it traces a different route, creating that loop. The size and shape of this loop tell us how much energy is lost, usually as heat or internal friction, and how much permanent change has occurred inside the material. This behavior is linked to the idea of material memory because the material remembers the maximum strain it experienced during previous cycles. When you stretch it again, it responds differently depending on how much it was stretched before. This is because inside the material, tiny defects called dislocations move and get pinned or rearranged during deformation. These movements cause internal friction, which makes the unloading path different from the loading path. Understanding strain hysteresis is important in many real-world applications. For example, materials that undergo repeated stress, like in bridges or airplanes, develop fatigue damage over time. The hysteresis loops show how much energy is lost each cycle and how the internal structure changes. Larger loops mean more energy is dissipated, which can be useful for damping vibrations but also indicates faster damage buildup. Smaller loops suggest the material is more resilient and better at resisting fatigue. Measuring these loops helps engineers predict when a material might fail. It reveals how the internal microstructure changes with each load cycle, giving clues about the material's durability. This is how strain hysteresis shows that a material has a memory of its past deformations. It's like a record of its stress history stored inside, influencing how it will behave in the future. So, in essence, the shape and size of the hysteresis loop tell us a lot about how a material remembers what it has been through and how it might fail over time.